Okay, so we left off last class talking about this new distribution. So when we kind of talked about this student T distributions where we have kind of a different distribution for every single degrees of freedom. Our degrees of freedom was just basically another way of saying, oh, there it is, n minus 1, right? Whatever the sample size is, minus 1. And this is kind of related to the idea that if we don't know the population variance, the best we can do is use this sample variance. And within that sample variance, we're dividing by n minus 1, right? And how much that's going to alter that depends on how large the sample size is, right? If it was 3, well, now we're dividing by n minus 1, we're dividing by 2 instead of 3. As opposed to if it's 1,000, we'd be dividing by 999, it's not going to change as much. So we had this student T distributions, right? One for every single degrees of freedom. It's still symmetric and the mean is 0, but the variance is going to be a little bit higher. So we said, if we're thinking about these different distributions, if I just use the old values I was finding from that standard normal distribution, well, now the area to the right of them won't give me the same amount, right? It won't be 0.025 here. Wow, 0.025 here, it's gonna be something larger. In fact, quite a bit larger. So we're gonna have to use a new table. Whenever we want a certain area in the tail, and here our confidence interval, I think we have a tail on each side. So if we want, say, alpha over 2 is 0.025, and our degrees of freedom was 50, this table would tell us that the T value we need to give us that desired alpha over 2 in the tail is 2.01. Okay, so it's the same type of setup we were doing before. It's just you have to use a slightly different table because these aren't the same distributions as we were dealing with before. Okay. We also said as we get really, really high sample sizes, right? If we could get to infinity, then our student T distributions essentially converge to a standard normal, right? So anything over 100, right? We can use that standard normal distribution really to approximate. Okay. So our final kind of equation that we're going to have here is going to look almost identical to what we were doing before with sample means. It's just now we'll build our confidence interval around that sample mean, but instead of a z value, we need to find a t value from that one of those student T distributions for whatever our degrees of freedom is, and of course alpha over 2 kind of being on either side. We also have the standard deviation of our sample means is now going to be denoted instead of sigma, we're going to denote it with an S here, because we're no longer using that population variance, we're going to be using whatever the best guess we have is, which is the sample variance. Okay. So if that's kind of our setup, let's start to walk through a few examples. Okay. So our steps are really going to be the same as they were before. The only thing that is going to be different is we use this student T value, and we notate the standard deviation a little bit differently because we're only using the sample variance. So let's say, just to put some numbers to it, let's say I've got 36 observations I take. I'm not able to observe the population variance, but I can calculate the sample variance to be 324, and the sample mean is 9. Right? So what if I wanted to, for this example, it doesn't have any context, but just to put some numbers to before we go to examples that have a little more context. What would the confidence interval be for the population mean that corresponds to an alpha of 0.01? So if alpha is 0.01, how much is on each side of our confidence interval? Well, we have 2 sides, so half of that. So we'll need to look up the area in the tail that we want is not 0.01, but the area in each tail would be 0.01 divided by 2. Okay. So 0.01 divided by 2 is 0.005. If our number of observations is 36, what would our degrees of freedom be? The degrees of freedom is simply n minus 1, or the sample size minus 1. Our degrees of freedom here would just be 36 minus 1, or 35. So we go to that student T table we have. The area that we wanted in the right tail was 0.005. Our degrees of freedom was 35, so we got to scroll down. Looks like right here. Go over. So the T value at degrees of freedom of 35, that would give us 0.005 in each tail, right, or in the upper right tail, is 2.724, okay? So we found that T value. or if I rounded this to the second decimal, but 2.72 or 2.724. From here, we can do the intermediate calculation, find the standard deviation of my sample means, just the square root of that sample variance over my sample size. I've got my sample size here, I've got my sample variance here. Now, one thing to make sure you don't do is here, when we're actually calculating the standard deviation, we're still dividing by n. So we're not going to divide by n minus 1 here, right? It's like n minus 1 is actually in this s squared, right? We just don't observe it. Okay? So I plug in my sample size, my sample variance, and now it's a matter of plugging in those three components into this confidence interval equation. Notice here I wrote in instead of the sample standard deviation for our sample mean. So we have here, so we go alpha over 2, right? You can think about it this way, but we know that we can write this as that. And we could also have written it as all these different ways of writing the same thing. So if you don't want to calculate that intermediate step, what you could do is just plug this formula in and do it all like on one line, right? Do this all at one time. Or you could calculate the intermediate step and then just plug in one value, okay? So there's two different ways of doing the same thing. It's kind of similar to what we were doing with the sample mean before. So if we do that, we get a pretty wide standard or pretty wide confidence interval here. So let's think about why. Well, if we look at the original population variance, the original population variance is pretty large. And so it's going to lead to, even with a sample size of 36, a pretty large standard deviation in terms of, if the mean is 9, our standard deviation here is 3. Even if we only go one standard deviation away, we're going to have a range of values that's what, 6, right? Go 3 to each side. Well, here, if we want to be able to say something with 99% confidence, that meant that we had to go 2.72 standard deviations above and below to build our lower and upper bound. So now when I multiply 2.72 times that standard deviation of 3, well, now I get a pretty wide range, right? I'm going almost 9 above and 9 below that sample mean, okay? So pretty wide range of values. Other than that, are there any questions over just kind of the mechanics of what we're doing here? It should feel really similar to what we were doing before. Like I said, really the only difference is this t value. So let's go through another one here. So let's say the American Medical Association, and actually, make sure, okay, I am recording. I get paranoid. So they state that the average, starting salary or the average salary for a physician is $175,000. You're not really sure. You want to test this. You go out and you randomly sample 81 physicians, and you find that their sample mean salary is $160,000. You calculate the sample variance, 324 million. If you wanted to build a confidence interval for what the true population mean is at an alpha of 0.05, which would correspond to what level of confidence? Alpha of 0.05 would be 95% confidence, right? Alpha is kind of the area outside of your interval, or the probability of being outside the interval. The probability of being inside the interval would then have to be 0.95, and when we're talking about confidence levels, we say them in percentages, so 95%, okay? If we look at these, it looks like 160 is kind of smack dab in the middle of all of them, so we can't really rule any of them out. From there, it's just a matter of kind of working through this, all right? So we've got an alpha of 0.05, okay? So what area am I going to want on either side of the interval? Alpha over 2. So 0.05 divided by 2 is 0.025. What's my degrees of freedom here? Yeah, if my sample size is 81, degrees of freedom is just n minus 1, so 81 minus 1 is 80. We go to that new t-table. We wanted 0.025 in one of the tails. We go down here to degrees of freedom of 80. The t value that we need to use is 1.99, or go 1.99 standard deviations above and below that sample mean that we saw to build our lower and upper bound. So We found that t-value. We write down kind of the sample mean, sample size, and sample variance we were given. From here, let's do the intermediate calculation. Let's just go ahead and calculate this standard deviation of my sample means. So I plug in my sample variance and my sample size, and I get that the standard deviation is about 2,000, right? So 324 million might seem kind of large, but we're dealing with salaries here. And if you take the square root, after we divide by sample size, we get about 2,000, okay? From here, we have everything we need, right? We've got our sample mean, we have the t-value, and we just calculated that standard deviation of our sample means. So we'll just go ahead, plug those three values in, right, and find that we have a lower bound of 156,000 and an upper bound of about 164,000. Right? Now, if the American Medical Association was claiming that the average starting salary is 175,000, what could you do with this confidence interval? You could go to them and say, well, look, with 95% certainty, I can tell you the average starting salary is not 175,000. It has to be one of the values in this range. In fact, we could probably go to the 99% level, right? It would widen this range a little bit, right? When we want to say things with higher levels of confidence, it'll push out the lower and upper bound. But my guess is even if we go to the 99% level, we're not going to get an upper bound that's above 175,000 based off of this sample mean that we found of 160, okay? So I'm trying to kind of get at this idea of like, how do we start to use these confidence intervals to, like, how do we interpret them or start to use them to answer questions? Kind of show their usefulness, right? We're not just computing them to compute them. Like we want to be able to tell, reject certain values as being the true population mean. Any questions on this before we keep going? Okay. Double check it. All right. So we worked through a couple examples there. Let's go back to this confidence intervals example file. And this first sheet that says unknown standard deviation and proportion. So let me zoom in here real quick. And we're dealing with this data set. We've got height, weight, gender, race identifiers. So the first one that we'll do is one we just talked about, right? So I'm going to delete this for a second. I'm also going to delete this, right? Yeah.
Holden and I were talking yesterday. How do you highlight everything and then delete it all?
Just highlight, okay. Like that?
Yeah.
So all I'm doing is left, just like I'm selecting the cell, and then drag my mouse.
Yeah, and then you just press delete.
So if you hit delete, yeah, it should erase everything for you.
Okay, because ours will only delete one cell, and it's when we select, even if we highlight everything. Because we were just like
Let me think how
baffled about how fast you could do that.
Okay, let me think what you might be doing wrong. Hold on. Why would it not work for you? Well, another way you can always do it is right click. It's going to shift on my cells though. Why would it not delete everything for you? Yeah, you should just be able to highlight, hit delete, and everything you have highlighted should get deleted. Is that not working? Really? Is there something else on your delete key? Like something written underneath it? Or no?
It's just like a backspace.
Okay.
Like,
oh, are you hitting backspace?
oh, that's probably why. Now I'm embarrassed. Hold on.
No, that's what you're doing. No, that's what you're doing. No, it's okay. Yeah, make sure you're hitting that delete key, not just the backspace key. I mean, some of the old laptops, that key's the same and you had to like hold shift or whatever, but yeah, so we'll highlight this. I'll just get rid of it real quick. So, I mean, hopefully at this point, I'm not going to go over. Hopefully we're comfortable that if I'm looking at column E, so I'm going to look at height here. The average function gives us the mean. That var.s now, right? We're using the var.s because it's a sample variance. We'll select that variable, and then we'll use that count function as well. So the count function gives us our sample size. var.s gives us our sample variance, and the average will give us the mean. So we've got the sample mean, sample variance, and the sample size. So one of the things that we're going to need during this process is the t-value that we need in our confidence interval. So with the normal distribution, I think it was either on Wednesday or Monday, instead of norm.s.inv, we're just going to use t.inv, right? So we're still kind of telling Excel we're going to do this inverse where we tell you the probability, and we want Excel to return to us now not a z value from the standard normal or norm.s, but a t value from that student t distributions. The area we want is alpha divided by 2. And our degrees of freedom, so the comma, the second thing we now have to tell the t.inv is not just the area we want, but what's our degrees of freedom? Well, here our degrees of freedom is our sample size minus 1. Right? Now, we have a very large sample here, so we're probably going to be able to get a pretty narrow confidence interval. Right? Higher sample sizes kind of drives down that margin of error that we're adding and subtracting. And so we're probably going to be able to get a pretty narrow range, would be my guess. Now, one thing I forgot to do is I saw a negative sign here. In my equations, I just want to deal with that absolute value, right? So what I can do is I can either use that absolute value function, or what was the other way we said we could do this? If I didn't want to use the absolute value function, if I know I want alpha over 2 in each tail, then this was where we said, if I want to go a certain number of z-scores, which now we'll think about them as, I shouldn't have wrote that in there. Also probably shouldn't use my hand. T-scores, right? If I know that I want alpha over 2 in the upper right tail, and I want to get just the positive of that t-value, well, the area to the left would just be 1 minus alpha over 2, right? So what we could do in Excel is instead of using the absolute value function, use 1 minus alpha over 2 there. Okay, so if I'm copying this down to do my other 3 alpha values, what went wrong there? What's going to happen if I copy this down? Yeah, right. I want to keep using the same sample size. I just want that cell reference for alpha to keep changing. So I've got my cell reference for the sample size. I'll put $ around the column and row heading there, or select it and hit F4 or FNF4 or Command T on a Mac. Hit enter. Now when I copy this down, now it keeps that the same and updates the alpha value. And we could do this not just for 3 alpha, we could do this for any alpha values we want to. Now from here, it's basically using Excel as a calculator, right? So my lower bound, I'll start with just putting the equation in there and selecting the things in that equation. So the first thing is take the sample mean, subtract whatever the t-value is, multiplied by the square root of my sample variance divided by my sample size. Okay. Now, if you wanted to, well, I'll go through this and then I'll show you another way we can do this. So same kind of thing. When I copy this down, I want the t-value that I'm using to change to correspond with different alphas, but I want everything else to stay the same. So I'm going to select this. test this. Okay. Okay, that's weird. So you guys can hear me now? Yes? Okay, all right. I don't know why, it's weird. Yeah, you should definitely check next time if you can't hear me. All right. Did it start from the beginning of class or did it just drop out? Okay, just did. All right, I was going to say. All right. So we'll go to share screen. So I don't know where I cut out. I think what I was mentioning was because we have such a high sample size here, look at how narrow we've gotten this confidence interval, right? With 99% certainty, I can say that the true population mean for height is in between 64.1 and 64.37 inches, right? And I think this is female height. I dropped it out just to kind of make a little bit more sense. But this is, this is the power of taking large sample sizes, right? I can really get a narrow range of values, okay? The other way I was going to show you, and I don't necessarily, I wouldn't probably do it this way, but if it makes sense and it helps you kind of keep track of things more, that's okay. And actually, I didn't really need to insert that. Hold on. I'll just put it up here. So let's say, instead of doing this equation all on one line, right? Actually, here, let me put this here. I could calculate that standard deviation of my sample means. So I could calculate this guy ahead of time and then just plug that in. So up here, if I said the square root of my sample variance divided by my sample size, right? Hit enter. Then I go down here. Well, remember, I was supposed to multiply that t-value by the standard deviation of my sample means, but I just wrote the equation in there, So instead, I could reference that cell where I calculated it, freeze it, because I'm always going to want to keep using that cell. Now, when I copy this down, I'm getting the same values, right? I'm just able to actually see what that standard deviation is. And one kind of neat thing about that is I can see that, when I have a high sample size, that drives my standard deviation down pretty low, right? But you don't have to do that. It's another way of doing it. I've seen people kind of do it that way before.
What was the calculation for that one again?
Oh, so we're just taking the square root of our sample variance over our sample size there. Yep. I mean, that's really what I have in here, right? I was just kind of cutting out that intermediate step. Any other questions on this? We're good? Okay. So one thing, I don't think I showed you an example of last class, or if I did, I guess we're going to get just another one because I want to show it to you here. So let's say I have this sample proportion. Oh, I know. Actually, we might have done this exact same one. Did we do one where we looked at the proportion of the sample that was white last class? I feel like I did. Maybe not. We'll do it again. So let's say I have this sample. I want to find what proportion of kind of the population is white or non-white. I've got this sample. I look at the sample proportion. It's about 0.5, right? How did I find that? Well, if I have a 1-0 variable, if I find the average or the mean of that, it'll essentially be a proportion, right? This is something that we talked about a couple classes ago. For the proportion, we can always use that standard normal. So we no longer have to use those t tables, right? We can use that standard normal. So norm.s.inv. What area do we want to look up? Alpha over 2. And then here, instead of doing 1 minus alpha over 2, I did the other way, which is you can just take the absolute value. Right? Both ways work. Okay? I just copied this down to get my 3 z values. And then from there, right, how do I get my lower bound when I'm dealing with proportions? So I take my sample proportion, I subtract the number of standard deviations the way I want to go, right? Or here, instead of a t value, it's a z value. And actually, to kind of show you the intermediate steps here, I would then multiply that by the standard deviation of my sample proportions, which the equation we had for that was the square root of the sample proportion times 1 minus the sample proportion divided by my sample size. Right? So it's a little bit different here because what this really represents in the numerator, it represented kind of my population or my population or sample variance of my proportion. So it's going to look a little bit different than the variance that we had for the means. But essentially, that's all that is. So it's the same format, right? Just these three things. If we want to remember, in Excel, they just represent. So for the proportion one, what we were doing there is this is all I was doing in Excel. I was just putting that equation and letting Excel do the math for me. You could find the values, plug them into your calculator and do it that way. But I don't know. Like I've said it probably a million times already at this point, but I just think it's so much easier when you have the values just to click on them in Excel than typing them into a calculator. Right? So now that we have this, right, when we copy it down, we don't want the sample proportion we're using to change. So I'll freeze that. And we don't want the sample proportion of the sample size to change. So we freeze those because all we're doing here is the confidence levels that we build are always going to be based around whatever the sample statistic we see is. It's just that we're doing it at different levels of confidence. So the only thing that should be changing is this Z value. Right? So I can copy that down to get my upper bound. I'll copy this, hit enter to get out of the cell, paste it, and then say, oh yeah, to get the upper bound, I add my margin of error instead of subtract it. Right? Then I copy this down. And now we're done. Notice one thing that's kind of interesting, and I'm actually going to walk through an example at the end of class just to kind of show you some more uses of this. Notice that even with a really high sample size, when we're dealing with proportions, we can actually, this is still, a range of 0.04, which might not sound like much, but when a proportion can only go from 0 to 1. So 0.04 isn't like the smallest kind of interval. And we'd have to take really high sample sizes in order to kind of get this interval even down to 0.04. Any questions over any of that? I know we worked through this last one kind of quick. Do you want to see another cell again or had any questions?
Can you click on the one to find the Z value?
Right here?
Yeah.
Yep. Yeah, so that's where, instead of using t.inv, because we're dealing with proportions now, going back to proportions, we could use that norm.s.inv. Any other questions? Okay. I think I have another example here. If you're just looking for more examples, where I do some more t-values. It's really the same thing that we just did, just with a smaller data set, different data set. What am I looking at here? I'm looking at drug deaths per 10,000 people. I don't remember why. So this is actually valuable. So let's say I wanted to do this at the 90, let's just do the 90% level, so alpha of 0.1. Could I say that drug deaths have went up in 2012 or 2006 compared to 2016? So sometimes you'll have a data set like this where it's separated out, so it's kind of nice. So I've got my drug deaths per 10,000 people in 2012, and here's my drug deaths per 10,000 people in 2016. So I went ahead, found the mean, the sample size, and my sample variance, right, var.s, for both time periods. I then built these confidence intervals at the 90% level. So in 2012, it was 2.16 to 2.73, 2016, 2.19 to 2.8. Well, if I plot these out, notice, you can see them. Notice that the upper bound in 2012, right, is still well above the lower bound for 2016. So if I was plotting these confidence intervals, there's a huge overlap, right? So it's going to look something like this. I think this was 2012, 2016s were a little higher, but there's a huge overlap, right? So it could be that the true proportion for 2012 was here, true proportion for 2016 was here, but it also could be true that it's instead over here, right? So when they overlap this much, or when they overlap at all, I can't really say whether or not drug deaths, the true kind of rate of drug deaths, was higher in 2012 or 2016. And I was writing these as proportions because I forgot we switched examples. These are clearly the population means, sorry. So with this in mind, where are we at in time here? 20 minutes? How much do I think we can get through here? We'll go back. I think this is interesting and worth our time. I reposted this set of slides, but I've got some new slides in there that I thought were kind of interesting. So we're dealing with these proportions, right? Which is where we had the standard deviation of my sample proportions. Here's that equation. Here's my confidence intervals, right? I think I had some old data last class. We're looking at the 2016 election, but I thought, let's try to predict the 2020 election, right? So there's a survey done by NPR. I got about 1,200 people, which seems like a pretty high sample size, right? 54% of people said they plan to vote for Biden. If we want to build a 90% confidence interval for what the true population proportion of people who are going to vote for Biden in the upcoming election is, well, we can do this, right? We've got our sample proportion, 0.54. We can look up that z-score. That gives us alpha over 2, which, what is alpha here? At the 90% confidence interval level, alpha is just 0.1. We look up alpha over 2, so 0.05. We'll always find that same z-score of 1.65. Now we've got our z-score. We can compute the standard deviation of our sample proportions by plugging in our values here. And then it's just a matter of plugging everything into that confidence interval. So we get this nice kind of lower upper bound where the true population proportion of people who are going to vote for Biden is somewhere between 0.51 and 0.56. Right? So as I'm saying this, I'm going to be drawing behind me, but I'm not going to keep switch. So because I need to see the slides because I keep reading. So 0.56, 0.51, and this is Biden. Right? So I looked at that same poll, but the percent of people who said they're going to vote for Trump is 43%, right? So now the only thing that changes is our sample proportion that we're looking at here is 0.43. So now we get this confidence interval of 0.4 to 0.45, 45-ish. Right? So we've got a scenario like this, right? So here's kind of Trump, this confidence interval, here's Biden's, right? What the 90% level based off that survey, what can I say here? Anything useful? So if this is the range with 90% confidence that I can say that the true population proportion of people who are going to vote for Biden is somewhere in this range. I can also say the true population proportion of people who are going to vote for Trump is somewhere in that range. What would have to be true? This proportion would have to be greater than this one, right? There's no overlap here. So even if the true population proportion was 0.54 for Trump, and even if it was 0.51, right? Those are the lowest and highest values in our confidence intervals. Biden's proportion would still be greater than Trump's, right? So I could say something like with 90% certainty that Biden's going to win the popular vote, right? I can't do anything with the Electoral College here, but I can do the popular vote, right? So, it's kind of interesting, but just as a general rule, I don't know. These polls are interesting. I don't know exactly the survey methods they use to get these 1,200 people, but I went out there because I know there was a polling or survey place that got it right in the last election was called Rasmussen. So they have a survey out there right now as well. They had 1,500 people, so a little bit higher of a sample size. Kind of notice, right? Dropped the standard deviation just a little bit. if I want to do a 90% confidence interval with this data, they found 51% of people are going to vote for Biden. So we use that in, factor this, so 0.48 to 0.53. They found the same 43%. So kind of interesting here, the Rasmussen survey, as well as this NPR survey, both found the same sample proportion. Now it wasn't exactly 43%, but very close to the same sample proportion. If we plug in all our values now here, this should be 0.47. This should be 0.43. Or sorry, no, this was 0.47. I had the typo here because Rasmussen found that the Trump was a little bit higher. So they didn't find the same. I lied. They didn't find the same one. I forgot that his is a little bit higher. I was copying and pasting. I forgot to change that there. So they found 47%. We build a confidence interval. Now notice the upper bound for Trump is a little bit higher than the lower bound for Biden. So really what we have there, if we plotted this out, is something that would look like this. Something that looked like that, right? So now we can't really say anything because the true population proportion for Trump could be here, Biden's could be here, or Biden's could be over here, Trump's could be over here. I mean, technically also Trump's could be here and Biden's could be here, right? It still could be that his is way higher, but we can't say at 90%, with 90% certainty whether or not that's the case because we only have one sample, right? We're basing this off one sample, okay? So it's interesting. Now, what would happen? We were doing this at the 90% level. What happens if I wanted to be able to make like that prediction of the popular vote with 99% certainty? What's going to happen to these confidence intervals? They're going to get wider, right? So now it's like, now I have even more of a range where they could be kind of, so I really can't say anything if I want to do it at the 99% level. So I don't know, I think it's kind of a, hopefully like giving you some insight. Obviously, like this is a business college. I know a lot of you probably don't want to go into politics, but in terms of like, you could do this with any survey data, right? You might want to know just the proportion of, maybe you're interested in like the purchasing habits of men versus women. There's a proportion of men who buy this product higher than the proportion of women, and we might want to target this, there's tons of applications, but with this is kind of a relevant one. I thought it was kind of fun to take a look at this, right? It also kind of points out that there's obviously I don't know, it's interesting to think about. We already talked about there's a lot of bias that exists maybe in some of these polls. But this is the point I made earlier in the Excel about even with 1,500 people in your sample, right? You still can't, this isn't that narrow of a range, right? 0.04, like, when we're talking about trying to predict the election, like if you're telling me that I've got a margin of error that's like 0.04, well, there's a huge crossover there, right? I could probably put money that I know Trump's going to get more than 30% of the vote, right? So I'm not really able to narrow it down a whole lot. I don't know what sample size we would need to really get it narrowed down. Probably one that's not feasible, right? I also had this thought, and I wanted to kind of see if you guys just kind of talk through it, so we can start to critically think about maybe some more complex issues. We'll use this example, but let's say I did want to make a prediction on this election about the Electoral College, right? Which way that's going to go. Well, that's based off of each state's vote, right? So what's maybe a way I could kind of use this idea of confidence intervals and comparing confidence intervals for different population proportions to predict the Electoral College? Let's start out small. How would I use this to predict whether or not Trump was going to get a higher proportion than Biden in Indiana? I basically do this exact same thing. I go out, maybe I find 1,000 people, right? I sample them. I then get the proportion of people in Indiana residents. I only randomly sample Indiana residents. The proportion who's going to vote for Biden and Trump. I build my confidence intervals. Hopefully, even if I do that, hopefully they don't overlap so I can even make the prediction, right? If I'm able to, I would then have to do that for every state, all 50 of the states. Well, I've now got, even if I did 1,000 sample size, that's now what? 50,000, I need 50,000 people in my sample now. So you can kind of imagine if we want to make these Electoral College predictions, man, our sample size would blow up pretty quick, because we would need pretty large samples in each state. I mean, notice here, if these numbers were for Indiana, right, and these confidence intervals did overlap, but we actually couldn't make a prediction for the election at the 90% level. We couldn't. Maybe we could do it at like the 50% level or something, you know, we could lower the percentage, but, you know, in order to be able to get these narrower, we'd have to take even larger samples from each state to make that electoral college prediction, which is why, you know, it's kind of hard to get these polls, it's hard to get it correct, right? Especially when things are close. If things are really far away, then it's a little bit easier, but if things are going to be close, it's a lot harder to make these predictions just looking at kind of these smaller samples, okay? All right, so got a little bit of time. I'll introduce kind of the next thing that we're going to talk about next week. So instead of scrolling, let's hypothesis testing. Okay. So I've kind of tried to set this up already with hypothesis testing. Sorry, with confidence intervals. But what hypothesis testing is we don't know where this population parameter is, whether or not it's a population mean or a population proportion. Right? So what we're going to do is we're going to develop a hypothesis, right? Kind of scientific method this thing, right? We're going to develop a hypothesis. We're then going to go out and get data and see whether or not we have sufficient evidence such that we can reject the hypothesis. Right? So if we, you know, think that the population mean, we develop this hypothesis that it's, you know, I don't know, equal to, you know, maybe we'll do income and say, is the mean income $50,000? Well, if I go out and take a sample and I see that from the sample, I get a sample mean of 45,000, I don't automatically say, oh, well, there's no way the population mean can be 50,000, right? Because it depends on the distribution of my sample means, which how big was my sample, right? What was my sample size? Because that impacts the standard deviation. So is seeing that 45,000, if what I assumed to be true was in fact true, that the true mean is 50,000, is seeing 45,000 enough evidence where I can reject that assumed true value of 50,000? That's essentially what we're going to try to do, right? Now, when I'm saying is 45, you shouldn't know the answer. We have to actually like develop like what are the steps in order to be able to say if what I'm assuming to be true, that it's 50,000, but I see a sample mean of only 45. Once we work through this method, like I show you the steps, what we should be able to say is I either with this sample can reject that assumed true population mean, or with this sample, I fail to reject it, right? It's not strong enough evidence to reject it, okay? So we have sufficient evidence, we reject. If we don't have sufficient enough evidence, we would fail to reject, or we do not reject that null hypothesis. So that null hypothesis is just referring to, that's what we're assuming is true. And the alternative hypothesis is then going to be essentially the complement of that. If I assume that the average income is equal to 50,000, the alternative of that is that it's not, right? That's not equal to 50,000. That's just the complement. So let's use this motivating example. We'll kind of set this up. So let's say I want to test whether or not the average mass market beer has a lower ABV than Bell's Two Hearted Ale, right? So Bell's Two Hearted, great beer. I don't know how many of you, probably a lot of you aren't 21, never mind. So I usually have like some juniors and seniors, and I forgot this is the honor section. So let's say, you know that it has 7% ABV and you want to compare it to the average mass market beer. You take a sample and you find the average mass market beer has an ABV of 4.5. Well, right off the bat, you might think, okay, then yeah, for sure. It's, you know, if I want to test whether or not it has a lower ABV than Bell's Two Hearted, looks like I found pretty strong evidence of that, right? But if I only took 36 and there's a high, you know, standard deviation of alcohol by volumes across mass market beers, then maybe I could see that, and it's not that unlikely I saw something that far away from 7. Without knowing the standard deviation, I don't know how likely or unlikely it was, okay? So the idea would be we want to develop a null and alternative hypothesis to test this, right? So the null hypothesis, what we're going to do, whatever we want to test for, we're actually going to assume the opposite is true. So if I wanted to see whether or not the average mass market beer is less than 7%, I'd assume the opposite is true, which is that it's greater than 7. Right? So it's almost like you're stacking the deck against yourself, right? So we'll assume that this is the true state of nature, or that whatever the null hypothesis is, we'll assume that's what's true. The alternative is just the contradiction of that, or like I said, you can almost think about it as the complement. Right? So we'll denote the null hypothesis as H kind of 0, and the alternative as H subscript A. Okay. Oops, there we go. So we can kind of have three different possibilities. Once we make these hypotheses, we can kind of have three different scenarios that we could see. So the first is that we found evidence from our sample that's inconsistent or goes against that assumed true null hypothesis. If it goes against it enough, like it's strong enough evidence that goes against the null, we can reject. We can also find evidence that's not consistent, or sorry. Here we go. So when we would fail to reject the nulls, when we find sample evidence that's not consistent, but it's not inconsistent enough from that null, right? It's like not far enough away from that assumed true mean. And then we can also have evidence where, what was I trying to say here? Do not fail to reject the null. Oh, obviously, if we find evidence that does support the null, so let's say I assume that the average income is above 50,000 and I find a sample mean of 55. Well, if the evidence is consistent with the null, then of course I'm going to, I'm going to assume, I'm not going to reject the null there, right? If the evidence is consistent with the null, then we'll decide to fail to reject as well, or accept, right? We never really truly want to say accept because we're still basing this off a sample. We just want to say we fail to reject. But you can think of it as when you fail to reject, you're really kind of accepting the null. Let me think. I might pick up on here next class. Yeah, we'll pick up here next class because I like this analogy and I don't want to kind of rush through it. I think it helps make sense of all this. So we will pick up on hypothesis testing next week. It gets pretty tough, I think. So I don't know. I'll try to move slowly through it. We're in a pretty good place in terms of kind of our progression in the course. So I'll probably take a little bit more time on some examples next week with hypothesis testing. The individual assignment is due at the end of the day today. Other than that, I will see you guys Monday. Have a good weekend. If you have any questions after class, feel free to ask. Oop, we got a question here.